In this video we're going to talk about the moments acting on the airfoil, and as you know it's extremely important for the stability of an airplane. And we're also going to talk about the special points in this picture, so especially for the center of pressure points displayed with the circle on this graph, and also with the aerodynamical center position displayed with the stars. Also, we're going to talk about the possible misconception in this subject, but first let's do the basic introduction to this field. Let's assume we have a distributed force acting on each panel element of this airfoil, and let's choose some particular point and compute the moment above this point. So for each panel we're going to have the corresponding elementary moment, and then we can sum all those moments and get the total moment for this particular point. So now let's assume this moment is known above some particular point, let's say a quarter of the chord from the tip of the airfoil. And now the task is to find the moment at any given location of this two-dimensional space. So how to find the moment at this point, at that point? And actually it's very simple, because the moment, the function of moment is linear with respect to the radius vector. So let's go here, those equations. So here's the elementary moment. So we have the elementary force and the radius vector going to this particular force, and then we can compute the total moment. So the total moment is simply the sum of all those elementary moments, and here's the equation. So as you can note that this thing is linear with respect to the radius vector. So now let's say we want to compute the moment at some other point. So let's basically move the coordinate system to that point and use the radius vector of this particular point of interest. So to find the moment, now you have to take a difference of those two vectors, and now the linearity of this function is actually plays a role, because when you take a cross product you're going to have two sums. So you have the original vector, and then you're going to have the vector where you're looking at the moment. So this thing is known. So here is the original moment given to us, and here is the moment that we don't know. And this thing can be basically rewritten. You can extract the radius vector, and then you're going to because the radius vector is constant for this particular point, and then you are going to have some of the elementary forces, and this will result in this equation. Very simple. So what you have the moment that is given to us, total moment, and then you're going to have the total force acting on this airfoil multiplied by the radius vector to the point where we are looking for the new moment, the cross product multiplied. And here is the final equation, and with respect to the aerodynamics, the force vector is proportional to the vector constructed from the coefficients. So we have drag and lift coefficients. So drag coefficient obviously on the x-axis and lift coefficient on the y-axis, and thus we can rewrite this equation in terms of the coefficients. So we have the moment coefficient at any point, so any point we wish, equal to the moment coefficient measured at a quarter of the chord or computed with XFoil, for instance, minus the cross product of radius vector going to this point of interest, multiplied by the vector constructed from the lift and drag coefficients. So all those coefficients are known. For instance, from XFoil software we know the total drag, total lift for the airfoil, we know the moment and quarter of the chord taken from the tip, and thus we can compute the moment anywhere, at any position of the space, here, anywhere. It's very convenient and very simple equation. And we can make the equation even simpler if we assume that we do not have any position. So the position of the y-axis is actually 0. In that case, the radius vector is simply a vector going along the x-axis, and because we have the cross product, the drag coefficient is not going to be, it's actually 0. It's going to be a 0 component where the drag coefficient is included. So in that case we have this reduced equation, very simple. So the moment coefficient stays the same, but then minus x multiplied by the lift coefficient, because the lift coefficient is normal to the x-axis, so it's going to make contribution to the cross product. Now let's see the results for the simplest case when y equal to 0. Later on we will see the results for the different positions, but now just for the simplest case. And we have the graphs plotted already. So here is NACA airfoil, so here is the moment value, and here is the position of the x-axis. So in each point of x-axis we have computed the moment and displayed with the curve. So the curves have different colors because they are corresponding to different angles of attack. So the blue color is for the alpha equal to 1, and the red is for the alpha equal to 7 degrees. So we have the moment curves, and you can note that those moment curves are actually linear because the moment is a linear function of the radius vector. So you can put radius vector anywhere in this position, but you're going to have the linear increase in the moment value. Okay, so this is clear. So how to plot those lines? We are going to use this equation. So we look at this equation. So here's our equation for the moments. And from this equation, what we can do, we can set x equal to some number, let's say 0, multiplied by lift coefficient, and then subtract from the moment coefficient taken at the quarter of the chord, and you're going to have the moment at the x equal to 0 position. The same, you can take the x, let's say at position equal to 1, and get the moment in this position. So thus you have 2 positions for the x and 2 positions for the moment, and that's sufficient to draw a line. So you're going to have a straight line. So you compute the moment at a position equal to 1 here. Let's say point is somewhere there, the green line, and then you compute the moment at the x equal to 0. So you're going to have the point here. So you can draw a straight line. And how do we know that we are correct? Because this curve is passing through the moments which are given to us by XFoil. So if you look here, so if you look at this graph, you will see that those lines are passing through the points that were given to us by XFoil software. So those are moment points at the position of quarter of the chord, and hence we have plotted those lines correctly. So what else? If you look at this graph, you will see that there is some interesting points. So for instance, when the moment is equal to 0, so obviously this point is a bit different for different angles of attack. Why different? Because you have different moments for different angles of attack given to you by XFoil. So different moments meaning that you would have to have a different position for the point where you have the 0 moment. So those points are called center of pressure points. So you have center of pressure points located on the x-axis, and you also have interesting points when those lines are crossing. So those points are called Aerodynamic Center. For whatever reason, let's assume that there is only one point, but actually those points are more or less closely packed, and you can actually look at the area of those points as Aerodynamic Center of the airfoil. So it's very useful because actually the behavior with respect to the angle of attack is a bit different. Like in this case, the momentum is growing when you increase angle of attack, but after this point, is the opposite is true. The momentum is dropping. So let's look at the graph in more details. So I have plotted this graph. So we have the airfoil, NACA airfoil. So from here we note that center of pressure is located almost exactly at the quarter of the chord, in small range around this area, and then also we have the aerodynamic center points which are also located very close to this position. So let's zoom into this range and see actually what the location for those points is. So the location of center of pressure points are on the x-axis, and it's very close to the quarter of the chord position, and the location for the aerodynamic center is a bit different. They kind of spread all over the place, but also are closely located to this position. So if you plot them the same graph, you will see that they kind of in a sense overlap. For this particular airfoil, for different airfoils you might have different results. And yes, so to find this point, how to find this point? You have to find the intersection point. So the easiest way, let's say you choose two curves. First curve is for alpha equal to 1 degree, and second curve is for the alpha equal to 2 degrees. So you plot those curves, so the blue, and then you're going to find the position where those lines intersect. So you can do it actually in a way analytically. So you know the curves for each line. We have just computed those curves in the previous step. So you know two curves. So after having two curves, you introduce condition that the y position is the same. So you have the intersection point. So this position will lead you to this equation from where you can deduce what is the position on the x-axis and what is the position on y-axis. So I've done this in the code. So I have those positions automatically, and those positions are computed for two pairs of lines. So between those two lines, and so on. So between alpha equal to 1 degree and 2 degrees, between alpha equal to 2 degree and 3 degrees, between 3 and 4, between 4 and 5, and so on. So we have those stars positioned here. So those points are called, once again, Aerodynamic Center. And now let's talk about some common misconceptions in this subject. For instance, some people think that those points, the aerodynamical center points, are located in single location. So it's not like many points, but the same point for all the alphas. And this is incorrect. For instance, let's look at this textbook. Oh yes, so I have finally opened the textbook because I want to make sure that my conclusion is not very strange. So this textbook, written by Anderson, Fundamentals of Aerodynamics, 6th edition, we go to the page 366, and we see this equation. So actually we do see the equation that we have seen previously. So I have the same equation, exactly the same. But then what he does, he do differentiation. So to find the focal point, the assumption is made that the moment coefficient is not changing with the alpha. So we differentiate this equation, and then we equate it to 0. So far so good, but now we have to differentiate this part. And he makes assumption that position of aerodynamical center is constant, does not depend on alpha. And this completely unbiased assumption. So if you do this assumption, of course, you're going to have the constant point. So the conclusion which he makes, that the center exists as a fixed point on the airfoil. And of course it's fixed point because just a moment before we have made this assumption that this point is fixed. But this point is not fixed. This point depends on alpha, and we have seen it previously. So if we are not going to make this assumption, biased assumption, then in that case you have to differentiate this function in the right way. So, well, actually he does not make this assumption, but he differentiates this part as if x is not dependent on alpha. So maybe a mistaken differentiation, but if you differentiate the function, which is complex, you have to differentiate it by parts. So basically differentiate the first function and the second one. So he does not make the correct differentiation. So I'm thinking that maybe he just made the assumption it's constant, or maybe he forgot the rule for differentiation, not sure. But as a result, we're going to have this incorrect conclusion. So let's do it in the right way. So we start with the same equation, and we differentiate the momentum coefficient with respect to alpha. So if you do that, you have to differentiate this by parts. So the first part, the second part, and then the zero momentum, the momentum at position 0, 25. Then we do the same assumption. So in the ideal case, you have those things constant, those differentials, and then you plug it to the equation and you get this equation. So and now you can see that this equation is non-homogeneous differential equation. So you have to solve this non-homogeneous differential equation to find the function of position of center of aerodynamical center as a function of alpha. So you have to do it, and if you do it in the right way, in the ideal case, when you have the simple conditions, so when you have the constant differentials for the moment coefficient and for the lift coefficient, you will end up with this equation. So if you solve it, you get the result for the ideal case, how the aerodynamical center depends on alpha. But in a real case, you don't make this assumption, so you're going to have actually this dependency in the real case, so the position of aerodynamical center is not constant, it's shifting with alpha. Okay, so this is the mistake made in the textbook, and actually I'm surprised because this is 6th edition, so I assume some people have read this book and nobody have paid attention to this wrong assumption. So maybe I'm incorrect, so if my derivation is incorrect, please let me know, because it's very strange. Book is well known and have many editions, and people are basically ignoring the equations in this textbook. So if I making something wrong, I would like to know it. Okay, so now I would like to talk about the mistakes I have made previously. So here is the graph. So my mistake was that there is a comment in XFoil which gives you the pressure distribution over the X and Y position. So what I did, I just, like when you have a hammer, like this code, all problems look like a nail. So I just use the power of Python to use this distribution of pressure of the airfoil to compute the momentum. Pretty simple. So you go from the pressure distribution to the force, so you compute the force with this equation: pressure multiplied by the length of the panel normal to the surface, and then you get the elementary force, and then you compute the total moment. But I completely forgot about the drag, because on each panel element you have the drag force acting. And you can get the drag force using some other command from XFoil, so you can extract the drag as well. So you have pressure and drag distribution. I think the drag is also available. So having the drag distribution and pressure distribution, you can compute the momentum in the correct way. So I just basically ignored the drag and got the results for the pressure distribution. So a mistake was made, and in my previous video I have incorrect graphs. Some wonderful people have brought to my attention that my center of pressure is located not at the right place, so now it's fixed. Now the location is exactly where it should be. I think the most correct way is to use XFoil, because in XFoil you have the ultimate reality, you have the real data, and then you have the real position of your aerodynamical center. And also we can look at the different types of airfoils. So let's say this is the NAC airfoil, and the position of center of pressure and aerodynamical center is close to the quarter of the chord of this airfoil. But if you look at different airfoils, let's say this airfoil is designed for the flying wings, and in the case of this airfoil, you have a bit different position of the center of pressure and aerodynamical center. So to be more precise, so here's the position of center of pressure. It's in front of the quarter of the chord, and the aerodynamical center is positioned behind this point. So in my view, this is more stable configuration. Maybe I'll talk about this in my next video. But the conclusion is that the quarter of the chord is a good reference point. You might have your center of pressure position exactly there or somewhere else nearby, and aerodynamical focus also can be positioned in some different places. And not only that, but also what you can do, you can compute the moment not on the chord line, because doing this on the chord line is a bit silly, but you can compute it anywhere, at any point in the space. So I have done this too. So here is the position of Y, and now the Y is very close to the chord line. Yeah. So here's the airfoil, and here's the actually the momentum curves on the line which is below the airfoil. So at this moment the line is a bit below the airfoil, and you have the distribution of momentum close to the 1/4 of the chord. You also have the zero, the center of pressure points, and you have the aerodynamic center points here and some of there. And you can do it for different locations. For your airplane, you can choose the best location of center of gravity. It might not be on the chord line of the airfoil, might be below airfoil, and you just look at those graphs and you pick the one that suits you the best from the point of view of stability. So I think maybe I'll make another video on this subject, but at this moment I think it's all become crystal clear, but the only one question remains. So please check your textbook and let me know what your textbook is thinking about the position of the aerodynamic center. So maybe this is a called misconception, so this position, and if so, we have to fix it using those simple equations.